Next up for our expert panel of scientists, we do have Dr. Matt Merritt, the Associate Professor at University of Florida. Matt Merritt received his PhD in physical chemistry from Washington University in St. Louis in the lab of Dr. Jacob Schaefer. His postdoctoral research focused on DNA structure elucidation with solid-state NMR in the lab of Dr. Gary Drobny at the University of Washington. His first academic position was NMR facility manager at UT Southwestern, working with Dr. Craig Malloy and Dr. Dean Sherry. He ultimately was promoted to associate professor before moving to the University of Florida in 2015. His research focuses on developing metabolic imaging methods and applying the technology to models of human disease, including non-alcoholic fatty liver disease. Without further ado, Dr. Matt Merritt's talk today is entitled Measuring Beta-Oxidation in the Perfused Liver with D15 Octanoate. And without further ado, I will let you share your screen, Matt, and take it away.
Thank you very much for the opportunity to present here. You guys have that screen?
Yep, we can see it.
Okay. Yeah, so this is all research that I've done here at the University of Florida, and it's my lab is really all about understanding intermediary metabolism and how it is perturbed in all kinds of pathophysiologies. And I'm very interested in fatty liver disease. And so I'm developing technology for imaging changes in liver metabolism in vivo. And of course it has stopped advancing the slides for some reason. Okay, there we go. So I'm going to talk about deuterium NMR. I've got a lot of experience with hyperpolarized carbon as well. And it's a great technique. You've got a large carbon-13 chemical shift that you can take advantage of. It's got the sensitivity that you need. There's no radioactivity, like the same benefit that you have with deuterium NMR, but you also need carbons that have a long T1, and you also need a polarizer that you've got a site next to a magnet, and so you've got that extra infrastructure cost. You can build one for preclinical experiments for next to nothing. But to do a human experiment, you have to purchase a system, and they run close to $2 million. So it was very exciting when this paper came out in 2018 from the DeGraff lab at Yale, where instead of using carbon, they use 6,6-deuterated glucose, which is one of the classic isotopic tracers that's used to study metabolism. And what they did was just administer the glucose and do straight CSI, and then went from the rat to the human in one paper. So that really gets your attention when something can translate that quickly. But what they noticed is that in the presence of cancer, the deuterated glucose makes a lot of lactate, the Warburg effect that's commonly understood in cancer. And so you can look at glucose uptake, glutamine, lactate, and then turns out that the lactate to GLX ratio was very diagnostic. I want to point out that imaging can cover over a lot of signal to noise ratio issues. That's not a great looking signal, but the image is certainly diagnostic, and that's what we really care about. Now, lactate was the object there, but I started thinking about other experiments that I've done with deuterated compounds, and I realized that the uniformly deuterated glucose, like Tatiana was just talking about using for structure elucidation, also generates a lot of partially deuterated water as it's metabolized. So you can see that not only are we making reducing equivalents that are deuterated, we're also producing HDO at phosphomannose-isomerase, triphosphate-isomerase at the enolase, exchange at lactate and alanine. So ideally, all of these would be one-way reactions. Some of them are exchange reactions. But if we're just trying to look for increased glucose metabolism, then HDO could definitely be a quantitative marker. And so I started doing experiments in Sprague-Dawley rats. I used the same dosage that Robin used in his initial experiments with the deuterated glucose. We just put a surface coal above the brain. And so this was from our first paper. You can see the natural abundance deuterium image, then the HTO versus the glucose after the injection of the D7 glucose. We just did a 2-point Dixon image. Just a classic fat water separation. But in this case, it was glucose and water. And so you can see that we get specific images here. The CSI might actually be superior for the image recon because the uniformly deuterated glucose has a lot of different resonances. So you get a lot of extra phase confusion, I guess is what you would say, because of those different resonances when you do the 2-point Dixon. But nonetheless, it was quite effective when we published this in Magnetic Resonance in Medicine in 2020. So now I'm going to talk about the liver. The liver is really the queen of metabolism. Almost any metabolic reaction that you can imagine is going to happen in the liver. It is a target of extensive hormonal control. It removes toxins from circulation. It produces glucose and it stores glycogen. And when you're fasting, it makes a lot of ketones. And the list could go on for about 5 more pages. But what I really want to focus on is thinking about how we could image fatty liver disease. So if you don't know, fatty liver disease is now believed to be present in about 33% of the US population, 33% of 400 million people. And it's benign, but it predisposes you for non-alcoholic steatohepatitis. The epidemiology is showing that NASH will be the #1 cause of liver transplant by 2025. I think it has actually already jumped up and is #1. The epidemiology could not keep up with the actual rate that it was occurring. NASH causes scarring on the liver. It predisposes you to hepatocellular carcinoma. It's just a major issue. And if you've got over 100 million people that have NAFLD, then NASH, even if it's 1%, that's a huge number of people that we want to be able to help out with their health care. And so one of the key questions is, when do you transition from NAFLD to NASH? And there's a reason to think about this, because the theory is that fat oxidation is very different between these states. And so I said, hey, can we do something to look at the rates of beta-oxidation in a model of fatty liver disease? So we've got standard C57 Black 6 mice. They were 16-week on a high-fat diet versus a low-fat diet. We excise the livers and perfuse through the portal vein using a standard Krebs-Henseleit buffer. We use 1 millimolar lactate, 0.1 millimolar pyruvate to keep that 10-to-1 redox ratio that you want to try to achieve. And we've got, actually in our column, we've got 2 reservoirs. And so we can switch on a reservoir that includes 1.2 millimolar of the deuterated octanoate. So why would you want to do the perfused liver? Well, it's a great place to start. You can control the nutrients that are available with very fine changes are possible. You can control the amount of insulin, the amount of glucagon. We're not using that here. This is just a straight question about beta oxidation. But all the hormonal signaling, you can actually add back and look at those effects on the metabolism. By doing this, we have a way to count the total generated HTO just by doing deuterium NMR. The other thing is that nutrient consumption and the products of the liver are easily measured in the effluent perfusate that comes off when you're doing the experiment. So we can do mass balance on these types of experiments. So I'll just jump straight into the data. The mice on the high-fat diet gained weight rapidly. Their mass went up. The liver mass went up. The oxygen consumption when we do these experiments are actually similar. You can see this is the absolute micromoles per minute, not normalized to grams. We'll talk a lot more about normalization in a moment. We did these experiments at 14.1 Tesla and with a NMR probe that was built by Q1 Tech. It's a 20 millimeter deuterium NMR probe that you can fit the liver in. And this is the type of data that you can get. So here is the normalized HDO signal. So the low-fat diet is making less HDO per liver than the high-fat diet. You can see that the high-fat diet livers actually accumulate more of the octanoate that we can see spectroscopically. But then if you turn around and normalize your HDO peak area to the weight of the liver, either just by the weight of the liver, the problem is there's a lot of steatosis, there's a lot of fat. So is that the metabolic weight of the liver? So you can normalize it to the total protein. It looks very similar to this. And what you see is that it flips over, and now the HDO is actually coming off less quickly in the high-fat diet. We take this really as a marker of beta-oxidation as opposed to TCA cycle turnover. That's because the HDO that's generated in the TCA cycle is about a quarter of what's generated by the beta-oxidation. They're all together, but this is really more about beta-oxidation than it is about the TCA cycle. You can take the HDO to octanoate ratio, and you can see that it's actually lower in the high-fat diet animals. Now, we wanted to come back and model this as accurately as we could. We're using Isotopomer network compartmental analysis. This is software that's freely available from the Young Lab at Vanderbilt University. It's an incredibly powerful tool. We've got here, wherever you see velocity, we also have a concentration of an intermediate that relates to it, because if you don't have the concentration of those intermediates, if you go back to your second semester of calculus and you were thinking about pouring salt water into a pool, what's the concentration of the salt in the pool after 20 minutes? You have to know the size of the pool. And so we have pool sizes, we have enrichments, deuterium enrichments, we have the HDO production. We also include models of the electron transport chain. And if you do that, you can break out these fluxes. And so one is just beta oxidation. So overall in the high-fat diet, there was increased beta oxidation. There was increased ketone production. There was a trend towards higher glucose production, higher anaplerosis through pyruvate carboxylase. Citrate synthase was low, fumarase was low. FADH2 was actually elevated, but strangely enough, NADH was not elevated, but there's a lot of FADH2 that's generated in beta oxidation. Now, if we normalize this to the liver weight, the story changes a lot. You see that there's actually increased beta oxidation, increased FADH2 turnover, but a lot of these things turn over and are not only are they no longer significant, but they can even reverse in their relative contributions. So what it's looking like is that larger liver is turning over more fatty acid, but when you normalize to the weight, the turnover is actually lower. So we're accruing damage is the hypothesis. We have lost the ability to oxidize fatty acids at the same rate because at some level we're losing beta oxidation, the function of that pathway. So there's many theories of NAFLD-NASH. There's two that I'm going to talk about. One is that in the fatty liver, you have impaired oxidation of fats, lower TCA cycle. You've got hepatic insulin resistance. And so there should be less fatty acid oxidation. if you think about it as an excess lipid burden that's associated with obesity, then the theory is that you drive excess TCA turnover. You therefore have increased reactive oxygen species causing damage. And that liver damage can lead to the NASH. So what does our data say about this? Well, I'm not making theory number 3 yet, because one, this is the perfused liver. Even though it's a very powerful tool, it's not in vivo. And so we really need to do this in vivo, and that's experiments that we're doing now. We're also using octanoate. Octanoate bypasses CPT1. CPT1 is the primary regulator of fatty acid entry into the mitochondria. So like I said, we're thinking about beta-oxidation. And so we're bypassing CPT1, looking at beta-oxidation. So this is not really a comment about increased fatty acid oxidation or not. We're talking about the specific pathway of beta-oxidation. So we've still got a lot to learn with this. This is the first metabolic imaging that we've done, still using a 2-point Dixon, which is actually a lot more effective for this tracer because the chemical shifts are better, but you can see that we get specific imaging here. The liver makes a lot larger signal than the kidneys do. Okay, so as a target of metabolic imaging, HDO in the brain gives you enough signal to use gradient recall echo methods. It's really nice. And we think that D15 Octanoate is going to be super powerful for looking at beta oxidation. I want to acknowledge lab members. These experiments were done largely by Mark McLeod, Dr. Raghavan, and Anthony Giacalone, who was our surgeon. Support from UF, the Mag Lab, the NIBIB, and thank you for your attention.
Wonderful. Thank you so much for a fascinating talk, Matt. Unfortunately, due to the timing, we're going to have to move along, but there are a couple of questions in the chat feature. If you would be able to answer them there, that would be greatly appreciated.